Yes, what's going on internet? Today on the workbench we have a very nice amplifier for you, and I'm going to guide you through the repair. If you have one of these, then if you are competent with a soldering iron and you know what you're doing a little bit, you have a bit of background on electronics repair, you have no problems fixing this if you watch this video closely. Digital Design's M4a, very nice piece of kit. However, this one doesn't do any power at the moment because it's in protection. So the customer who gave this to me said that he was playing at low volumes and he heard a loud bang from the amplifier, and then it was in protection mode and no longer playing audio. He said that there was no smoke from the amplifier, just a very loud bang, and then some things were rattling around inside the amplifier that he noticed. So if you watch my videos, you will already know what parts of the amplifier are damaged and probably what parts aren't. But if you're new here, then we're going to guide you right from the start as to how to diagnose why this thing is in protection mode and then how to get it out of protection mode. The first thing that you need to understand is the amplifier has two completely separate sections. The power supply section, which is always closest to the power input terminals, and the output section, which is actually doing the amplification. This is the bit that's actually taking the audio signal and amplifying it for the subwoofers. All the power supply section is doing is taking 12 volts and turning it into a high voltage rails, or a couple of high voltage rails, for the amplifier to actually use. If your car provided the correct voltage to the amplifier section from the start, you could have an M4a that was only this big. You wouldn't need any of this stuff. But because cars are 12 volts and obviously we need much higher voltage for the amplifier to work, we have this great big section here which provides the power to the amplifier. Now, when the power supply section blows, because these are the MOSFETs which are on the power supply section. The MOSFETs are the things that actually do the power. So these are the things that are actually passing the 12 volts and giving it to the transformers to turn it into something bigger. So when the power supply section blows, these MOSFETs, they short. So they have three legs, like these over here have three legs. MOSFETs have three legs. And these three legs all short together most of the time when the amplifier blows. Now these MOSFETs are connected to, the middle pin is connected to the positive power input, and the outermost pin is connected to the ground. So what happens if all three of these legs short together? You essentially have a short circuit across your power terminals, which is very bad news. And that's why sometimes when your amplifier blows, you can see that the voltage absolutely dives, and you see like 9-10 volts, because all of a sudden there's pretty much a dead short circuit across your power terminals. Now when this happens, the short across the power terminals is actually a short across all the FETs, and so the FETs just kind of turn into a light bulb and heat up like crazy and start smoking. So if you think you've got all of these MOSFETs here that are basically like cooking up, they release all the magic smoke, and that's why when an amplifier blows the power supply section, even after you've turned the amplifier off, you end up with plumes of smoke and nasty smells, and that is the power supply MOSFETs dying and cooking up. So because when the power supply FETs blow, they almost every time will short out those pins. A pretty reliable quick test method to know whether your power supply section in the amplifier is damaged or not is to take your multimeter, just a basic, doesn't have to be an expensive multimeter, can be anything, and turn it on to continuity settings, so it gives you a little beep when there's continuity between the probes, like so, and then just put it probes onto the power terminals of the amplifier, and you should see that it beeps initially and then starts to climb the numbers on the screen. Actually, if we go, so this one didn't beep this time because the caps still had a little bit of charge in them. So what's happening now is I'm just swapping the orientation of the probes here, and that's why it's changing the numbers there. So you see there that the capacitors do have a bit of charge in them, and the multimeter is essentially charging the caps, which is why the numbers climb. So the fact that we don't have a short circuit across these power terminals most of the time will mean that the MOSFETs don't have short, which means the MOSFETs haven't died, and if the power supply MOSFETs haven't died, then the rest of the power supply drive circuit is probably fine. When you hear a large, loud bang, a crack from the amplifier, that is generally high voltage, which is shorting. A loud, sharp pop followed by no smoke, is generally the voltage in the rail capacitors which are dumping through the output FETs, and that is the sharp big bang that you hear is a high voltage short. If the power supply shorts, because it's a lower voltage, you'll generally hear more of a poof, like a sort of soft, like a poof, and then followed by fire loads of smoke. So because this was a big loud crack, I think that we have output section failure and the power supply is okay, and we have pretty much confirmed that by making sure that we don't have a short circuit across our power terminals. Power supply is probably fine. So let's turn our attention to the output section. So just a little bit of visual inspection first. A loud pop could either be a capacitor or a MOSFET. Now this amplifier, someone put some pictures up of this amplifier and loads of people said, oh, it's the capacitors. Guys, it's never the capacitors. In these new amplifiers, these capacitors, they never die unless there's a flyback effect caused on the output inductors, which I won't go into now, but 99% of the time the caps are fine, and if they're dead, you bloody well know about it because they'll spew their guts all over the board and you can see it instantly. These are fine. If you think these are slightly domed, they're actually not. What these caps have is they have a plastic kind of, almost like a dust cap on the top, and so it looks like maybe they're bulging, but actually it's not. It's just the curvature on the plastic top to the capacitor. These caps are absolutely fine, no problems there. The loud bang was actually caused by this output MOSFET here exploding, and you can see there that the MOSFET is lacking the front. That has fired off into the amplifier, and there's also another one over here which has lost a lot of the front of the MOSFET there. So we've got one MOSFET there and one MOSFET there with obvious visible damage. However, don't instantly assume that the parts in the amplifier that don't show any visual signs of damage are okay. No. Electronic components do not generally show visual signs of damage when they fail. It's just by luck and chance here that these two output FETs here that died, they died in such a dramatic way that they blew the fronts off. However, I would guarantee that this FET, and this FET are also shorted out and damaged and can no longer be used. I'm not sure how well this camera will make it out, but I noticed as well there's also a hole in this driver IC. Can you see that? It's the one on the far end, on the far right. There's actually a hole in the chip, and that is actually the chip which is responsible for driving this bank of output MOSFETs. So that makes perfect sense. So looking at this amplifier so far, my diagnostic is power supply absolutely fine. What happened is that this drive chip just decided to die, which they do. They are very delicate and they're a bit like a light bulb. They only have a certain amount of lifespan, and especially when they're run without a heatsink. Sometimes these chips really are best run with a heatsink attached to the front of them. So these chips are just run on their own like this. They run pretty hot, and if it's a hot day as well, then they run pretty damn super hot, and they can just overheat or just fail spontaneously. And when these chips fail, then they will short out and they will send a big spike to the MOSFETs, which is what we see here. The big spike probably has been sent to the gate of the MOSFET, turned it on fully, and therefore the contents of the rail capacitors has been suddenly dumped through these FETs and exploded them. So let's start taking the amplifier to pieces and see if my diagnostic is correct. So that's the board out. Now, first things first, we're going to want to remove everything from the board that we find that's dead. So because there were some exploded MOSFETs on this side, there's two options here that we could do. We could either just replace the bank of MOSFETs, or two banks if this bank is dead as well, that have failed, and leave these ones, which are probably fine, in the board, and leave the chips for those in the board that are probably fine. That's one way of repairing it, and that is a cheaper, quicker repair. But because this is such a lovely amplifier, I've given obviously the customer the option. I always give the customer the option to either just repair what appears to be damaged in the parallel banks and whatever, or to do a complete refresh of the output section. So in this case, the customer wants a complete refresh, and that means changing all the FETs out and all the drive ICs and the bootstrap circuit, so that it is pretty much brand spanking new as far as the output and drive circuit goes. Just like I explained before, the way to determine whether these FETs are dead or not, and obviously the ones that have holes in are obviously dead, but we're going to take our multimeter, put it onto continuity setting once more, and we want to measure between the legs of these FETs. So if we go between 1 and 3, which is the gate and the source, these are the ones that usually shorts out. And yeah, we have direct continuity. We have a beep on the multimeter and it's showing 0 0 on the screen. So yep, we have a dead MOSFET there. This one's also dead. This one is showing 71 ohms. That's either dead or, oh yes, that is definitely dead. So that's so dead that it's no longer a short, it's just it's come apart fully. So yep. So yeah, we're gonna go ahead and replace obviously all these ones, but we're gonna replace every single output MOSFET on this amplifier as per the customer's request. Now the ones further along on this amplifier, this other bank here, because this amplifier works in banks, so we have, most bass amplifiers do work in banks. So as you can see here, we've got 4 output inductors. And the reason we've got 4 output inductors is we've actually got 4 separate amplifiers here, all parallel together. So essentially all this is you've got 4 drive chips on the driver board, and you've got 4 output inductors and 4 sets of output MOSFETs. You've got, 1, 2, 3, you've got 3, so on the output section here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 MOSFETs on the output section here. And these are split up into banks of 6. So we've got 6 on this inductor, 6, 6, and 6 on each inductor. And of those 6, they're split up into 3 high side FETs that drive a high side, and 3 low side FETs that drive the low side. And this is what creates the sine wave. So we've got 1 amplifier, 2 amplifiers, 3 amplifiers, 4 amplifiers, all paralleled together after the inductors to drive the 1 ohm load. And each amplifier part has a separate drive chip that drives it on the driver board. And they're all fed with the same input signal from the RCAs. This is important to know because sometimes if you're having difficulty with the repair, your drive waves look good and you put the FETs in and everything goes wrong. What you can do is you can lift the output of each of the inductors to disconnect them from each other so that they are no longer paralleled, so that each amplifier part is separated from everything and it's just not connected to anything. So remove the output of the inductor from the board, just lift it off the board, don't have to take the inductors out fully, and then you can run the amplifier, and each of the amplifier quarters will run independently of their own, even with the FETs in. So then you can read the output waves of each of these quad amplifier sets and see if the waves look the same. They should all look identical between these 4 because they're being paralleled together. If one of them looks different or has a different dead time, or the wave looks a weird shape, then you know that you have issues on that one that's causing the weird shape. And then once you've repaired that, you can put them all back together, put all the inductors back in the board, and then it should run fine. So let's just see about these ones that were on the board over here that haven't visually exploded. Do we have a short circuit? No, we don't. So these ones are probably fine. So I think my diagnostic is probably correct in saying that all that happened is that one drive chip exploded and decided to take out just this amplifier, just this one here with these bad FETs on it. So this quarter of the amplifier got taken out because the drive IC exploded, but all the other 3 sections of this amplifier were unharmed. However, because these are all parallel together, it's good practice if you're doing this anyway to replace everything so that it's all the same chip batch and all the same FET batch. And the fact that this chip just exploded, that potentially means that the other 3 that were put on at the same time maybe are on their way out as well. Maybe they're reaching the end of their life, or maybe they've been slightly weakened by this situation as well. So it's a good idea just to change everything when obviously the customer gives you the go ahead to do that. And a lot of the time I have customers that will say, no, don't worry, just replace what's dead, and then obviously maybe 6 months to a year down the line, if it blows again, then we repair it again, and it's an additional cost then for the customer. But it depends what the customer wants to do at the time. Sometimes they don't want to pay out up front, sometimes they'd rather pay for a cheaper repair and see how it goes, and then most of the time those amplifiers just last, they just work for years. It's the chances of these other 3 sections of the amplifier being absolutely fine are quite high. Is quite a high chance that these didn't get damaged at all in this situation, but there is a small chance that they did, and there's a small chance that the amplifier wouldn't be as reliable or work for as long as it would if we went ahead and just replaced everything. So in this case, the customer wants me to do replacing everything, so that's what we're going to do. So we've removed all of the output FETs and also removed the drive board. Now if you haven't removed the driver board before, then try it first on some small cheap amps you don't care about, because you need to learn how to remove these effectively without damaging the traces or pulling the vias or lifting the traces or anything like that. When it comes out, you should have a nice clean set of legs with no orange stuff attached to it, no vias or no traces or pads stuck onto the legs, and you should have a nice clean board like this that doesn't have any of those rings missing or any of the traces lifted or any vias missing. Very, very important, super important, because stuff goes from the top of the board to the bottom, and if it doesn't get there because there's a damaged via, then you're going to have a bad day. So very, very important. Learn how to remove driver boards. This was a specifically tricky one to remove, very, very tight in the holes, and I had to use all my skill and experience to remove this nice and carefully. It took a little while, but we got there. So yes, all of that has been removed. So now, because all of the parts which we have measured as damaged have been removed, that being the output MOSFETs and the drive chip, the drive board here, what we can do is we can actually apply some power for the first time to the amplifier and make sure that the power supply section works correctly, and make sure that the output rails build as they should, and that we have the correct small voltages for powering the drive card, and that's like the plus minus 15 volts and 5 volts and plus minus 12 volts. You can also check with your multimeter on continuity setting that there's no shorts between either of these two. These are voltage regulators. These are, I think, probably the 15 volt ones, and these are the 12 volt ones. So just make sure that these aren't shorted across their legs. Other things to check for: make sure that these green things, which are actually their inductors, make sure these read around 5 ohms. Sometimes they can read 2 ohms because there's 2 in parallel, so make sure they read around 2 to 5 ohms. There's a couple dotted around here on the drive circuit section and the voltage regulation circuit. And then also make sure that these source resistors are around about 1 or 2 ohms on the multimeter. You got 2 there and 2 there. You'll generally see 4. You'll see the same number of these source resistors as you have inductors on the output board. That's just the general quick stuff to check with your multimeter once you've taken the drive board out. Make sure that the gate resistors for the bank that went down, these green gate resistors, make sure they all read the correct value, in this case 47 ohms. So to apply some power to this board, I'm not gonna bother putting the wires in fully. I'm just gonna pop them into, there's some handy little holes here on top of the terminals. When we power the board up like this on the bench, we barely need any current at all to run the board in its idle state like this. So what we can do is literally just pop some wires on there for easy removal, and it also restricts the current a little bit. And I also turn these amps on with a lowish voltage into the amplifier because this lowers the output rail voltage to make it safer to work on, and it gives you a bit more time if anything is heating up before it explodes, so if you can notice it. And also we don't need much current. I'm probably going to give this thing about sort of 6-7 amps just to turn on with. It's a relatively big board, so we want a little bit of current, but not too much. We want lots of time to notice if there's any faults on here. So let's go ahead and turn our scope on. So what we want to be looking for is that when we touch the back of the power supply FETs, you'll see that the it bumps up to our input voltage, which in this case is 10 volts. When we apply some remote to the amplifier, which I've got on a foot pedal just for convenience, you can see that a square wave starts to build on the scope. I'm going to let you zoom in here to the scope, and we can see it'll glitch off a little bit first. So I'm just going to pulse the remote for like literally a fraction of a second. Just like that, and you'll see that it will draw some current from the power supply. There'll be a faint rough sort of like thing of a square wave that appears, and then obviously we remove the remote. Now after you've done that one pulse, you can actually go ahead to the output section and see the rail voltage start to rise after you did that pulse. So if I now probe the output section here, you can see that just that one tiny little pulse put 4 volts onto the positive rail, and then 4 volts onto the negative rail, 4.6. So what we can do is just go ahead and make sure that that rail voltage is in the correct places. Like I said earlier, we have 4 output amplifiers that are parallel together, and they each run on a high side and a low side to drive the output. So the high side will always have nothing on pin number 1, high voltage rail on pin number 2, and nothing on pin number 3. So you should have 3 high side FETs, so 1, 2, 3, and then the next 3 should be low side. The low side always has on number 1 negative rail, 2 nothing, and 3 negative rail. So just to recap that, high side has nothing, positive, nothing, and low side has negative, nothing, negative. very important that that is the case. If you see any voltage on pin number 2 of the low side or pin number 1 and 3 of the high side, then there is something on the board that is shorted. Most likely you have a solder bridge. When you were desoldering these FETs, most likely you have a solder bridge that's connecting some of these pads together, and go ahead and check for that before you power the board up properly. We've only got 4 volts on here, so it's very safe because we just pulsed the remote very slightly there. If you have voltage where there shouldn't be when the driver board is in, then that means that you have a bad drive IC or bad something on the driver board that is the problem. If you have the driver board removed, then there really shouldn't be any voltage where there shouldn't be. So let's go ahead now and turn this on fully, and let's probe the power supply, and I think the power supply is working fine as we just did that pulse and it seemed to be okay. So let's go ahead and turn it on fully, and we see there the square wave gets bigger and bigger. And then the current should taper off, and this thing, so the amplifier draws 2.1 amps at 10 volts worth of input without any FETs or without any driver board in. Cool. So yeah, the power supply is absolutely fine. We've got a nice square wave here. I'm just going to go ahead and check that is the case on every single one of these FETs. And just like we had in the output section, the power supply, we've got 6 transformers, which means that we have 6 little sort of banks here that work together in a push-pull configuration. Each transformer has 2 FETs which drive the high and 2 FETs which drive the low. It's not really high and low, sorry, it's just different phasing. So you have 0 degrees and 180 degrees in terms of drive, and that pushes and pulls the transformer like this, which then gives you the output wave, which then goes to these rectifiers. Now these rectifiers, they're not FETs. A lot of people get confused and think these are FETs. They're not, they are rectifiers. All they're doing is they are taking, if I turn my scope up a little bit, they're taking the output of the transformer, which is obviously a very, very high AC square wave like this, 120 volts, and then it turns it into a negative rail DC and a positive rail of DC. That's all they do, and these incredibly rarely die. You never have to change these. They will show a short if you get your multimeter and you try and read across 1 and 3. Don't do it when there's voltage in these caps, but if you do it when the amplifier is empty, you will see probably a short circuit across some of these pins. It's not actually a short circuit on the rectifier. All you're doing is you're just reading the coils of the transformers. So forget these. These are always fine. Very, very rarely do these get damaged, and it's like a kind of last resort thing. If it's not working and drawing current, then they're the last things I check. They never die. So yeah, cool. Power supply works well, and we just had the amplifier running then. We can see now if we go to the low side and high side, we've got negative 78 volts on our low rail, and we've got positive 76 volts now on our positive rail. So that seems good. The amplifier is happy with everything that we have on the board at the moment. It's not drawing excessive current, nothing is getting hot, it's staying pretty cool. Once you've turned the amplifier on and done your checks and powered it off again, don't touch the board, because these rail caps still have plus minus 100 volts on them, so that's 200 volts worth of potential, which is gonna flippin' hurt if you touch it, and it's gonna cause a big spark if you short something out and possibly cause damage elsewhere on the board. So don't touch the board. Stick your probe in one of these to monitor the rail voltage. So it's now down at 70 volts, so we lost 30 volts already, and just you can either go and make a cup of tea or maybe make a cup of coffee and wait for that to sink down slowly back down to 0 volts, or you can take a dummy load like a big resistor and you can short across the rectifiers which have those 2 rails on them, and then the voltage will go down to 0 volts. You need a pretty big resistor to do that. I would say something like 40-50 ohms is fine. It'll take a few seconds to go down to 0. If you use something too low, then what will happen is you'll get a spark and the resistor might explode, because you're basically dumping capacitors which have an incredibly high potential output current. Their ability to output high current is immense. They just boom, the internal resistance is nothing. So if you run a low resistor on these caps, then that resistor is just going to get overloaded, get hot, maybe smoke up and explode. So yeah, just use a high value resistor to keep it within the resistor's tolerances, and it'll get the rail voltage down to 0 nice and quick. Or you can just wait for the amplifier does have pull down resistors inside it naturally anyway, and that's why the rail voltage is currently sinking down to 0 on it of its own accord. See, we're down to 39 volts now, which is fine. Once it gets down to about 20 volts, you can take a pair of pliers and just short it out yourself. You get a little spark, but it's no big deal. Alright, so let's put our main amplifier board to one side for now, and let's concentrate on the driver board. Now, this may look daunting, but it's quite simple once you understand what's going on. The driver board, you will need to work on this if the output section blows most of the time, because as we can see here, one of these chips has a hole in it. Now, to replace these chips, really you need a hot air reflow station, which I've got here by AOUA. So you need a heat gun like this, and you need to be able to obviously aim it accurately at the chip and monitor the temperature on the hot air reflow station, set the correct temperature, and then use some tweezers to lift the chip off, refresh the solder pads, and then put the new chip on. So yeah. The things that most commonly die on these driver boards are the chips, and you can tell if the chip is dead because most of the time, if you power the amplifier up like we just did, with the driver board still in, then you'll see that there are rail voltages on some of the pads where it shouldn't be. Like it will either be on the center pad, you'll have some negative voltage on the center pad of the low side, or on the high side you'll have some negative voltage on 1 and 3, and that will be because the chips have shorted out. So that's the easiest way to check whether the chip is dead or not, is to slowly power the amp up with a little bit of voltage, just pulse the remote and get the rail voltage up to like 10 volts. And if you see any voltage on any of the pads where it shouldn't be, the chip is probably dead. If there isn't any voltage on the pads where it shouldn't be, but you don't get any square waves or they look really bad, then the chip is probably dead again. Other things that commonly die on these driver boards are these bootstrap diodes and capacitors here. If they die, they will most likely go to a short circuit. If you have drive issues after you fitted the FETs, you can't figure out where it is, try changing these parts anyway, as sometimes they kind of halfway die and they cause issues. Other parts that die sometimes, but not as commonly on these driver boards, are these little 2D transistors, these SOT23 parts up here. In rare cases, you'll find that these resistors and capacitors are burnt out, and these are responsible for all sorts of things like setting the delay, turn on delay for the chips, setting the dead time of the drive waves, and so on. So these need to be perfectly intact, but they don't often die. In this case, they're intact. You know, if they die, then these resistors will be burnt out. You better see it. So I think in this case, we probably on this amplifier only need to change the chip, and let's just check the diodes here, make sure, see what these are saying. So these should have nothing on the multimeter one way round, and the other way round they should have a value something of 350-ish. I've got 387, that's correct, and the capacitors should have nothing on them. They should show nothing open one way, and the other way they should show nothing open one way. So yeah, that looks good to me. Just make sure that none of these other ones are dead. I don't think they will be, seeing as this part of the amplifier survived. Cool, so it looks like we only really need to be replacing this one chip. However, because we are doing a complete refresh on this amplifier, we're going to change all 4 of these chips for the customer so that it is as fresh as it can be. What you really want to do is preheat the board first, so just take the hot air gun and just sort of draw circles around the general area that you're going to be taking the chip off. The reason for that is because where the board is cold, if you just dump it on the chip like this, then the heat will sink away into other parts of the board and the solder won't melt as easily, and you'll just end up burning part of the board that you're aiming at. So if you preheat the area that you're going to be working on, then it helps the solder melt a lot easier and prevents you burning one specific area of the board that you're trying to get super hot and it's just sinking the heat elsewhere. So I think we're ready now, so now I'm going to aim it generally at the chip. I'm still going to keep a little bit of movement in there because I don't like to hold it in one place. You can burn a specific spot on the board where the heat accumulates. So let's just keep doing little circles like this, and already the chip is very much ready to come off. Just pull it off nice and quickly there. There we go, nice and easy. And I'll do the other 2. Oh yeah, and for those of you that haven't done this before, these chips, the model numbers are masked off. However, it's quite easy to find out what these are from Perry's Guide or from other places on the internet. These chips are called IRS21844S. So IRS21844S is the chip number for these. So once you've removed all 4 of the chips, we want to go ahead and refresh the solder pads on there. So I'm going to go ahead and take a small tip on my soldering iron and lower the temperature slightly. I don't want it too hot on these tiny pads. I'm going to go to about 370 degrees there. I don't know how accurate my AOUA soldering station is for the temperature, but 370 generally works really well for this stuff. So I'm just going to go ahead and wait for this to heat up. And we're just going to touch on the pad, apply a touch of solder just to get a little bit of a blob there, refresh it nice and good. You don't have to be too careful with this because obviously the solder has flux in it, so you can go ahead and just, you know, wipe it over, and any solder bridges that you get will come off when you wipe over it again. You don't have to be too careful. Just make sure that once you finish like this, there's no solder bridges left, and each of these pads has a nice little ball on top. There we are. So once the pads have been reflowed, we just want to go ahead and preheat the board a little bit again before getting our new chip. And you want to make sure you get the orientation correct for the chips. Very important, otherwise you'll damage all sorts of things on the board. You see there that there's a small arrow right by the one of the pads there, and that is pin number 1. And on the chip, you'll notice there is a small dot where pin number 1 is. So you want to line the dot up with the arrow. And lower her on. My hands are a little bit shaky. There we go, nicely done. Just want to angle her a little bit more central. There we go. Push down on the chip and let it cool. There we go. And repeat 3 more times. There is one thing to bear in mind when doing these chips. They are quite sensitive to heat, and if you cook the chip up for too long, you can damage the internals of the chip and it won't work properly, or it'll blow the second you put power to it. So you want to just make sure the board is nice and hot before you put the chip on to minimize the amount of time taken heating the chip itself. And then when you lower it on, just keep heating those pads, keep moving your hot air gun around, and then once it's on, just a couple of seconds more heat, shift it into place, push down on the chip and let the heat gun away for this auto set. And yeah, there we go. I don't think you'd ever know that these chips have been replaced. If you're not 100% confident in your hot air station soldering and you're not sure if the pins have actually made a good connection, you can go ahead and take your tweezers and you just want to try and push each pin a little bit, and it should not move. The pin shouldn't come away from the pad, it shouldn't like go off to the side. If it does, then obviously it wasn't connected properly. There should be quite a strong connection to from the pin to the pad here. So if you can push the pin to the side, then it's not connected properly and you need to go ahead and redo it. If you can't get it right with the hot air soldering station, you can very carefully with your soldering iron with a very small tip, you can go ahead and solder each of the pins manually like this, and you want to make sure that you heat up the pad first and the pin. So put it on there for a couple of seconds until you see the solder melt, then add a touch of fresh solder and you should see it flow up the pin and onto the pad. You don't want to put loads on because you'll end up with a bridge across these pins, and then that's a headache and you've got to get rid of it. You've got to use some solder wick and get rid of that. Yeah, it's a bit annoying. So just try and use the hot air station where you can. If it's not looking reliable with a hot air station, then turn to this, but just do it very carefully. Of course, once you fitted the chips on there and you're confident that none of the bootstrap diodes or capacitors or anything else on there is shorted out, go ahead and grab the main board once more, and we are ready to slot that back in place. So just line this up, make sure you get it the right way round. Most time the board has markings on it for which way round this driver board goes in. So whack it in, flip her over and resolder to the main board, nice and easy. Cool, so now we're ready to power the board up again, but this time rather than just looking for rail voltages, we are looking for square waves. We're looking for a drive wave on some of these pads on the output section. Now the only pads that will have a drive wave on them, a square wave, are going to be the low side gate. So remember earlier we looked at what was the high side and what was the low side. So the low sides were the ones that had negative rail on 1 and 3 and nothing on 2. So the only pads that are going to have any kind of square wave or drive wave that we can check are going to probably be the low side drive. So that's going to be the low side gate, which is pin number 1. So there'll be 6 pads on this side that have a drive wave and 6 pads on this side that have a drive wave. The high side gates, although they do have a square wave when this is fully reassembled, they don't have a square wave without the FETs in. They need the FETs in to have a square wave on the gate. Some amplifiers will give you a square wave on the high side gate if you lift the inductor leg, like I suggested earlier, but we don't need to do that, provided the low side drive wave looks good. Most of the time the high side is also good. So let's go ahead and apply some power once more, and let's watch the rail voltage sink down to negative rail, and the square wave actually rise along the negative rail, which we'll see in just a moment. Okay, cool. So there we have the negative rail starting to build. Let's take it to the scope screen. Okay, there we go. So you can see there's a little wave there. There we go. So that's what we're looking for. We're looking for a square wave that looks a little bit like that. What we can do is, if our scope is good enough, actually most scopes will do this, you can turn your scope to AC coupling, which only shows AC things, so it negates DC, and then we can zoom in, go back to 2 volts divide, or 5 volts divide actually for this amplifier, and then that square wave should appear nice and big on the screen. There we go. It's a little bit noisy due to my scope setting, so if we turn noise rejection on, there we go, looks better. It'll probably bounce around a little bit because it's trying to drive something that isn't there. So this is what's called a self-oscillating amplifier. So there needs to be the feedback loop needs to be complete for the frequency to be set correctly. So at the moment this is oscillating at about 2 kilohertz. When the FETs are in, this will probably oscillate somewhere around 150 kilohertz or above, or maybe 125. Between 125 and 200 kilohertz, it'll probably oscillate with the FETs in. So we want to make sure that this wave is nice and good and present on all of these low side pads. So we're going to go ahead and check. So we've got the high side here, which won't have anything on it. It'll probably have a few glitchy things like this where it's like attempting to drive it but it's not there. The low side should have the nice square wave on it on this bank as well, and go over to the other side of the board, this bank and this bank. So there's 4 banks that have the square wave on it and they all look identical. That's a good sign. So when you get to this point in the repair where you have a good looking square wave like that on all 4 banks of these low side gates, then you're pretty much ready to go ahead and fit the new FETs. I forgot to mention, some amplifiers, even if everything's perfect, when you put the driver board back in with no FETs, you don't get any square waves on the gate pads of the low side, even though everything's fine. Some amplifiers require a RCA signal in order to produce the square wave on the gate pads of the low side drive. So if you think you've repaired everything properly, you've powered it up with the drivers all in, and you don't get anything on the low side drive, then run like 40 Hz sine wave into the amplifier's RCA inputs, and you should then see a 40 Hz square wave. So you have to turn your scope to a different time divide to see the 40 Hz square wave on the low side drive gates. Okay, so the FETs are all in, the drive board's back in, so the amplifier is fully reassembled, and before we add any power to the board, it's a good idea to just do some quick checks with your multimeter. You want to go around each of the banks of FETs, so you've got high, low on one side, high, low on one side, and you want to just make sure that the multimeter diode setting readings are roughly the same for each of the banks. So if we turn our multimeter to diode continuity setting once more, very useful setting this. So what we want to do is we want to put our probes between the gate and the source, which is 1 and 3. And you'll notice that they have different readings depending on which way round you put your probes. So one way round you'll get a high value up in the 1500s, and the other way round you'll get a lower value down nearer sort of 3 to 500. Wait for it to finish charging. It'll probably jump up in a minute to 5 something. There we go. So you want to make sure that this rests somewhere, well, generally somewhere between 3 and 600. So this is obviously one bank of 3. If we go along and check the next, so we got high side, low side, high side. That's how this amplifier is configured. So high, low, high. So the two high side banks on this side should be the same with around about 600. So if we go ahead and check the other one. Yep, that's the same. And let's check the two low side banks. 584 and 582. Yep. And let's check the other side. High side bank should be about 600. Yep. Other high side bank. Low side bank. And other low side bank. Yeah, looks pretty good to me. They're all pretty much the same reading, and that shows that the drive circuit is equal and there's not any leaking between any of the FETs or anything like that. You can also check between all of those with the multimeter probes the other way around as well, just to make sure that there are no differences in reading there, but I'm pretty confident in this repair. This is a really simple repair, nice and easy, just drivers and FETs, nothing too complicated going on here, so this should be nice and easy. So now we're ready to power her up and apply some power. Now, because Class D amplifiers, they don't generally like being powered on sitting idle without any speaker connected. And the reason for that is because across these speaker terminals, it actually kind of completes part of the feedback loop a little bit. And sometimes if you leave an amplifier idling for too long with nothing connected on the speaker terminals, then it can actually spontaneously blow up. So just for precautionary method, I'm going to see if I can find a 47 ohm resistor. Here's one. Just to put over the speaker terminals, just because it's a good practice. I don't always do this, I will admit, but it's a good practice to show you guys and to just explain that Class D amps generally don't like being powered without anything on the speaker terminals. So let's put a 47 ohm resistor across the speaker terminals, if I can fit it in here. There we go, 47 ohm resistor, and let's take our multimeter probe. Now we're going to allow a little bit more current to pass this time because we're enabling the Class D switching on the output section. So I'm actually going to go ahead and allow, what are we on, 6? I'm going to go ahead and allow 8 amps to pass, just over 8. That should be enough to get the amplifier up and functional. And I'm actually going to use 2 probes for this test. I'm going to enable channel 2 on my scope, and what I'm going to do is turn them both to 50 volts divide, and I'm going to clip channel 1 onto the low side drain. Now the low side drain will have a nice big square wave on it, provided everything works correctly. And the other probe, I'm going to go ahead and look at the high side rail. I'm going to look at the high rail, just so I can see the rail charge, and then I can see the square wave come into play when it activates. So let's go ahead and probe the drain of the drain of the high side and the drain of the low side. So if you probe drain of high, drain of low, then on the scope you'll get two waves, 2 lines. You'll get one which is just the positive rail voltage, and then the other one will be the square wave, which is the output of the low side FET. So let's go ahead and show you my scope and power her up and see what happens. There you go. You can see the voltage rail rising, and we have Class D output switching. We've got only drawing 4 amps, which is perfect from the amplifier. It's really nice low current draw for an amplifier this size. Very good circuit design from DD on this one. This is a generic board design. However, DD would have tweaked and perfected this to make sure it meets up to their high standards. So that looks really nice. And that was with 10 volts worth of input. However, the real test is whether this thing works at 14 volts, because sometimes issues can arise when you start increasing the rail voltage. And just to make sure, I've actually got a thermal imaging camera here. I want to go ahead and look down this and make sure that none of these FETs are heating up. If one or more FETs are getting hot when the amplifier is idling, then it's not good, and we have a problem that we need to look for. They all look stone cold at the moment, so that's good. So I'm going to go ahead, I'm going to do it in stages. I'm going to crank her up to 12 volts next. I'm going to power her back on with 12 volts to make sure that it's happy. There we go, looking good. Yep, we've got 143 volts worth of square wave. This is getting kind of scary now. I really don't like working with these crazy high voltages. But yeah, the FETs are staying cold once more. So the final test is to bump this up to 14.4 roughly, and turn it on once more, and it should stay cold and operate without exploding. I really hate doing this because I hate these big amps with these fucking crazy high voltages, but let's go. Yep, there we go. 169 volts on the rail, on the switching, and we have a positive rail voltage of 147 volts. So yeah, it looks nice. And looking down the thermal imaging camera here, the only things that should get hot on the board are these resistors, because these are like to do the rail resist, they're pulling down the rail voltage, so they generally run quite hot. There'll be some resistors over here by the rail capacitors which will get hot, that's normal. The driver board will generally run a bit warm. The drive ICs generally run at about 40 to 50 degrees depending on your input voltage, so I'm happy with that, and I think we have a successful repair here. So the next thing to do is to reassemble this into the case, and because we can't actually drive a load with it out of the case, the FETs gets too hot. So we're going to reassemble into the case and then do a bench test to full power, provided my power supplies will cope with it, and then run a 45-minute endurance test to make sure that it's solid. There we are back in the case, and it's always a good idea to do one last power up on the small supply first before you plug it into the large supplies for the bench test, because if anything has happened whilst you've been assembling it, a small bit of solder has fallen somewhere, or one of the FETs is shorting to the heatsink that you're not knowing about, a small hole in one of the thermal pads for example, then hooking up to the big supplies will cause a catastrophe. So we're going to go easy with the small supply one last time. Now it's in the case, make sure that the repair is solid, and then we'll go ahead and do the full bench test. There we go, nice big wave on the screen, and amps clicked into operation with the green light on the side. Where's the green light on this thing? There it is. Nice, I like it. And there she is, in wicked mint condition I have to say, on the heatsink. Beautiful, beautiful amplifier, and a very good, very nice, well established board design that has been around for many years, 15 or so years, but with the tweaks that DD has made to this board, I'd say this is a strong contender for one of the best amplifiers in its power range in terms of reliability and a accurate musical bass reproduction. So I can't actually bench this to clipping point on my current power supplies in the workshop because they just trip out. It's too much power, it's a freaking beast. But I do get loads of power out of this, right as much as the power supplies can provide, into the static load. So I know it's solid, it does good power, and I've been running it on about half power for the last half an hour, and it's staying pretty cool, and it's, you know, it's really doing well. So just to show you it working, because it's kind of boring looking at a wave on a screen, I thought I'd hook it up to this woofer that I've been working on. This is a hybrid between an SPL Dynamics, I can't remember the exact model number, but it's 1500 watts RMS as standard, and it's the same coil, but all it is it's just on an Orion HCCA 10-inch motor. So this is the motor from a 10-inch HCCA with the SPL Dynamics parts on top. That's pretty cool, pretty big motor compared to the original, so I thought we'd hook this up and show you some excursion just to show you the amplifier working good. Yeah, nice. I'm pretty happy with that. That's playing the woofer nicely. I'll continue the endurance test for a little bit longer, but I'm pretty confident this is a nice, easy repair. We've done a full refresh, so there shouldn't be any reason that there's anything wrong with it now. So yeah. Guys, I hope you enjoyed the video. You've probably got lots of questions about some bits and pieces that I've been going through. If you don't regularly watch my repair videos, then I kind of skipped over a lot of stuff. So if you'd like to ask me any questions, just drop me a message to my Facebook page. Just go to Facebook, search for BearVids, comes right up, or facebook.com/BearVids, or my NSV page, go to Facebook and type in NSV audio. You can also ask me a question there on anything to do with amplifier repair. Videos of my Z415s in the van are coming very soon. Oh my god, it's fucking insane. It's loud as hell, it's insane, it's crazy. I've wired up a second LW amplifier, a 4.5K, strapped to the other one at 0.5, so each amp is seeing 0.25, and they love it. The inductance and the impedance rise is so high on the Z415s that the amplifiers are actually seeing probably a higher load than they were on the 35s at 1 ohm, which is just insane. So yes, and it's flipping loud, it's stupid loud in fact on the two amplifiers. It's really made those Zs come alive, and I think that we are on our way to 156 dBs or so. The next thing I need to do is sort out the batteries, which I've just done. I've just bought 4 Stinger 2150s because that's what fit in the space. I'm going to get a massive alternator, twin alternators on there, probably about 400 or 500 or 600 amps worth of alternators on there, and I've got my bank of super caps, 2 banks of super caps devices. It's really made those Zs come alive, and I think that we are on 15s, but it's already insane even on the leisure batteries, the lead acids that were in there before. It's even crazy on those. So when I get the Stingers wired up, it'll be even better, and then eventually it'll be on even more power than the two 4.5Ks. But yeah, stay tuned for that. If you want to see more of that, subscribe, click the bell icon so you get notified when I am live and when I post a new video. Until next time, take it easy.